Cool. So let's start. Hello, everyone. Welcome to today's bootcamp on Homework 2. So we'll be covering both Homework 2 Part 1 and Homework 2 Part 2. We'll be starting with Homework 2 Part 1, and in the second half, it will be about Homework 2 Part 2. So before we start the bootcamp, yeah, it will be good if everybody puts themselves on mute because there is a lot of disturbance. Yeah, so before we start the Homework 2 Part 1 bootcamp, what we expect is people have gone through the CNN lectures and have also attended the previous recitation, which was on convolution neural networks, and most importantly, have also gone through the write-up, right? So as you guys would have seen in homework one part 1 write-up, so it was very descriptive and gave many details for the implementation. So homework 2 part 1 write-up is also similar. Here we have added multiple diagrams and key points and steps wherever required for it to become much more clear for the students who are implementing, right? So it is very important to go through the write-up very carefully, right? So let's start. Yeah, in today's homework 2 part 1 bootcamp, basically we'll be talking about few key points which are very which one should keep in mind before implementing the class. Basically, it might be some tips, and it might be some of the common mistakes that students might do when they are implementing the class, right? And we do not necessarily intend to explain each concept in this bootcamp because we expect that people have gone through the lectures and the citations beforehand, right? So yeah, that's what the homework 2 part 1 bootcamp will be about. So moving forward, let's first check that what is the objective of this homework. So basically doing the homework 2 part 1, we will be able, the students will be able to implement all components of CNN from scratch. So, sorry, any questions? Yeah, so all components of CNN from scratch, implementing convolution layers, pooling layers, downsampling, upsampling layers, and both the forward pass and the backward pass for all these components, correct? So this is the basic objective of this homework. Moving forward, let's check the first thing that you'll be asked to implement. So this basically gives the first few pages of the write-up gives you a background about convolution, etc. The first question that the first part you will be able to answer is, let me scroll down quickly. Yeah, these MCQs are important. It will give you a clue about important formula, etc. for implementing various parts of the homework. After implementing the MCQs, the first class that you will have to implement is the upsampling 1D and followed by the downsampling 1D, correct? So in upsampling 1D, what you're expected to do is basically given an input and an upsampling factor. So say we have been given an upsampling factor of k. What we want to do is basically append k minus 1 zeros in between any two values of the input. So in between this 1 and 0, say if my upsampling factor was 2, I am supposed to add 2 minus 1 zeros in between this. So that's what you see here, 1 0 and then again this particular value, right? So that is what the expectation of this layer is. So basically add zeros, k minus 1 zeros in between any two elements of the input, right? So that would be the forward pass. Coming to the backward pass, if my upsampling factor is again k, and in this case, say the k is 2, so we will be dropping off k minus 1 elements from the input. So in this fashion, so if you have 1 0, 0. So every second, then fourth, then sixth element will be dropped. So say if my upsampling factor was 3, so k minus 1 in that case would have become 2. So in that case, then I would have dropped second and third element, retained the fourth element, and dropped the fifth and sixth element. So it's quite intuitive. So that's what my that's what my backdrop of upsampling 1D would look like. One thing to keep in mind while implementing upsampling 1D forward and backward pass is that your input size, whatever, if your input size is say n, the DLDA which you would return from the backward pass should also be same as the input size. So this is one of the mistakes that many people might do, that if their input size is say 6, their DLDA might, their DL and upsampling factor is say 2, the DLDA that they might be returning is 5. Right? So there might be loss of information in some cases where when returning back the DLDA. So keep in mind that the DLDA that you return is the same size as your input. Correct. So the next thing after upsampling 1D is downsampling 1D. It's similar to upsampling 1D. So in the downsampling 1D, you will be dropping off the elements with a factor of k. That would be the forward pass. So, and in the backward of downsampling 1D, you will be adding elements with a factor of k. So one thing to note here is that the upsampling 1D backward is nothing but downsampling, right? And downsampling 1D backward is basically upsampling. Both are reverse of each other. So yeah, you can use that and make your so there's a question, only one dimension increase in upsampling 1D. Yes, so only one dimension increase in upsampling 1D. So keep that in mind, that upsampling backward is basically downsampling and downsampling backward is basically upsampling. You can use that while writing the code for this resampling layers, right? So once you have that for upsampling 1D and downsampling 1D, the upsampling 2D and downsampling 2D are very much similar. It's just that rather than having to add or drop elements in one in just the horizontal direction, you would be dropping off or adding elements in vertical direction as well. So in case of upsampling, rather than just adding zeros in the horizontal layer, horizontal direction, you will be adding zeros in the vertical direction also. So you'll be having like a 2D input map, and then you'll be appending zeros in this way. So you'll still add k minus 1 zeros provided your upsampling factor is k. Correct. So everything stays the same in the case of 2D. Is just that you will have to consider adding or dropping off elements in both the directions, right? Width and height.
So do we need to reuse the 1D version for this?
Not necessarily, because what the input that you would have is would have like the width and height both. So while dropping off, you will have to consider dropping this and this. I mean, both in both directions simultaneously. So I don't think you can reuse 1D, but the concept is similar. It's just that in 1D you would have just written code to drop in one direction. In this one, you would drop in both height and width, right? So you'll have batch size, in channel, width and height, right? So you'll have to drop elements in the last two dimensions in case of 2D.
Okay,
yeah.
Thanks.
Yeah. One quick note is that the write-up was updated day before yesterday. So this formula, which you see here below figure 11, page number 18. So this was updated and such that it works for both input size of where input size where the width and height might be even or odd. So yeah, you can download this write-up again. Right. Cool. So similar to as in case of upsampling 1D and downsampling 1D, you need to make sure that if the input map size is m cross n, your DLDA that you would be returning should be of the same size m cross n, right? So make sure that there is no loss of information when you are implementing the formulas, right? So that's about resampling. Next, let's move to convolution. Are there any questions in resampling before we move to convolution neural networks?
I had a question.
Yeah.
So in the lectures, as it's explained in the lectures, when we upsample, we'll have to increase the number of channels. So we'll be doing this here as well, right?
Increase the number of channels. No, this is for. No, you will not be doing anything to the number of channel. So if so say this is the shape, right? N, C, H0 and W0. So what after you upsample, say, only the H0 and W0 will be affected. So say if I'm upsampling by a factor of, if my input is 1, basically no, 1 batch, 1 channel, and 3 height and 3 width. And if my upsampling factor is 2, then my output will still remain 1 cross 1 cross 5 cross 5, because I would have added 0 in the second place and the fourth place. Yeah, so that is these two will be increased. Nothing will happen to the N and C.
Okay, got it. Thanks.
Yeah. So yeah, let's move on. So in the convolution neural networks, first thing which we'll be implementing is Con1D. So in the Con1D, first thing which we'll be implementing is Con1D with stride 1. Right. So this is the first diagram of forward, and it's very, very explanatory. Basically, this is the input, and at each step, it shows that when we traverse with this filter over this input, and then so this filter is over at this place, we multiply the values of input at this place and the filter, and then add those values, then what will be the final value? So after that, if I add a bias of 1, what will be the final set? Right. So this is single channel. It's very, very self-explanatory. What we'll talk about a little bit is.
Please mute your mic.
Sorry. Yeah, what we'll talk about today is this particular diagram, the figure 14, right? So some students had this question, so we'll talk about this. So in this particular diagram, this is Con1D with multi-channel input. So if you see here, A, right? So this is a multi-channel input. So in this particular example, A has 3 channels and is of size 1 cross 5, right? Similarly, this is this particular filter has 3 channels and the size is 1 cross 3, right? So do not confuse this particular diagram with Con2D, right? This is Con1D with multi-channel, right? So please mute. Yeah, so that was one thing that I wanted to highlight here, right? So this is example of multi-channel. So what happens in multi-channel is, if I have an input and how do we traverse over with the filter, right? So if my input is like so, I take my filter and keep it over this position, right? I multiply corresponding values of my input channel 1 and the channel 1 of the filter, and input channel 2 of the filter, and so on. And then for all, since my output channel is 1, so basically output channel depends upon the number of filters that I have. So if we see here, I mentioned that there is only 1 filter and that filter has 3 channels, right? So my output channel is 1. So my final output is basically summation of all these values. So that is how you get 4, right? That's how the calculations work. So similarly, when I move the filter here and multiply the input with the filter values for all the channels and add up all of that, I get this, right? So this is how we are expecting you to understand this particular diagram, right? For clarification. This was for clarification. Let's now see that how would we do a backward pass for a multi-channel 1D case, correct? So in the backward pass, we'll be having DLDZ, correct? So what is the first step? Once we have the DLDZ, we'll be broadcasting it similar to the size of the W, right? And then to get DW here, yeah, to get DLDW here, the calculation is a little bit different, right? So suppose my DLDW, I keep it over this position, the first position. I would multiply 1, 0, minus 1 with 2, 1, 1, right? Whatever value I get. So here it will be 2 plus 0 into 1, that is 0, plus minus 1 into 1, minus 1. So that is 1, right? So, and sum it up, and that would be my value here. So in the previous forward pass, how we saw that it, since there were 3 input channels and 3 channels in the filter, we basically added the values over all the channels, and that was what we stored, right? So here it's not the case. Since we have broadcasted, do not look at it as a multiple channel case. So we are essentially multiplying this DLDZ with this much, this 1, 0, minus 1, adding up and then storing the value. Similarly here, 0, minus 1, 2 gets multiplied with 2, 1, 2, and this is the value, right? So that's how you are supposed to implement, interpret this. Yeah, we are just trying to tell this because it might be a little confusing looking at the previous diagram and this diagram. So yeah. So in case of backward, how we do is basically we'll have the weight matrix from before. We'll flip it horizontally, right? Since this is the con 1D case, we'll do only horizontal flip. So in the lecture, I'm sure you guys would remember that in case of 2D, we flip horizontal and in vertical direction both. So since this is my weight matrix, it is one filter with 3 channels. We and con 1D case, we just do a horizontal flip, right? We horizontally flip, right? And then don't forget to pad zeros. So kernel size minus 1 zeros on the left and the right. So this is another common mistake that people might end up doing. So append zeros and then convolve, right? So that would give us the DLDA. Another point to notice, again, the DLDA size and DLDA shape should match the shape of input. Right. So these are few key pointers when working with multi-channel inputs and multi-channel weight matrices. Correct. Any question in Con 1D stride 1?
I have one question about the matrix A multiply DLDZ.
A multiply DLDZ. Yeah.
Yeah. So I think I missed something on the class. So why do I have to calculate such an element-wise product? So example 1 multiply 2 and 0 multiply 1 and minus 1 multiply 1 goes into the very first element of DLDW.
So you're saying that why are we multiplying this part with this part and then adding up to get this element? So that comes from the equations, the convolution equations that we write for. So forward equations you will have A into W and then get C, right? So in the backward pass to get DLDW, you will be essentially multiplying A and DLDZ.
I understand. Thank you.
Yeah, cool. So once we have con 1D with stride 1, con 1D with stride greater than 1 is as simple as, so the way we are trying to interpret stride greater than 1 in this homework is basically in each case where stride is greater than 1, we first perform a convolution with stride equals to 1 and drop the elements. So if my stride is say 2, I will first perform a convolution with stride 1 and drop. If my stride is 2, I will drop every second, then fourth element. So that would essentially give me the output that I get if I do a stride 2 convolution, right? So yeah, so basically, while implementing the convolution with stride greater than 1, what we would expect if you would have seen in the starter code. So once you have done a con 1D stride 1, con 1D with stride greater than 1 would essentially involve you calling the con 1D stride 1 forward followed by downsample, right? And in the backward case, you'll be calling the corresponding backward functions, correct? So that's how you'll be interpreting stride greater than 1 in this particular homework. Yeah. So this was about con 1D stride 1, and since most of the things remain similar in con 2D, we'll not be talking about it in this particular bootcamp. Only thing which we want to keep in mind is that what in con 1D, what we were doing was we were just moving the filter in one direction, horizontal direction. But in case of con 2D, we'll be moving the filter both in horizontal direction and in vertical direction, right? So rest of the things remain same, and all the calculations, the way we were doing in con 1D, would remain the same. I would recommend to everybody to go through the write-up. And if anybody has any doubts, they can come to the OH to clear those, right? So Mansi, can you go next?
All right, so we looked at the normal convolutions right now. There is another functionality that we would want you to implement, which is transpose convolution. So basically, transpose convolutions are used whenever you want to have your output map to have a size that is greater than your input map. So there are networks in which you would want to sort of, you have your input image and you downsample it by using convolutions and pooling, and then you have a feature vector, and then you want to again go back to your original spatial dimensions, which is the equivalent to your input size. So in order to go back from that smaller feature vector to your original dimensions, you would have to use something like a transpose convolution, where you would go on increasing the size of your output map. So this transpose convolution also can be thought of as a series of operations. One thing that you could do is use your already implemented upsampling layer, followed by your stride 1 convolution. So these are some of the examples, as you can see. So this is for the con 1D transpose forward. You would first be upsampling your input, and then you would just do con 1D stride 1 forward. And the backward, you'll have to call the backward functions in the correct order in order to implement it. So basically, this class would not involve a lot of coding. You will have to reuse the existing functions that you've implemented till now. Similar, so this was about con transpose 1D. Same thing you'll have to do for con transpose 2D. Just that you will have both the width and the height dimensions in this case. Next up, we are going to look at, so the flattened layer is, I mean, it's pretty self-explanatory.
I had a question.
Yeah, go on.
So regarding the transpose convolution, it says that the main operation is to upsample the input and then convolve with stride 1, right?
Right.
But isn't that what we were doing in the previous sections too? Or like, I'm failing to see how is it different?
So in the previous sections, what you were doing is that you did like a con 1 convolution stride 1, right? And then followed by downsampling.
So in this case, what happens is your size of the output map is going to be smaller than the input map, right? Whenever the stride is greater than 1.
Okay.
Yeah, but in case of transpose convolution, you first upsample your input map, and then you do a stride 1 convolution. So that's going to result into an output map which is larger in size than your input. So it's exactly opposite of what we did in the previous sections.
But so why is it called transpose convolution? Because there's no transpose.
Well, there is no transposition done in this case, but yeah, I understand your question. So there is a layer in PyTorch that's implemented in this fashion, and it's called transpose convolution. The way in which that functionality is slightly different from what we are doing in the homework, but the main crux lies in this particular operation where you do an upsampling followed by a stride 1 convolution. So we have like picked up the name from the PyTorch's implementation. So yeah, maybe you can go and look that up, but make sure that, this is a slightly different version of the implementation. It's not exactly the same as PyTorch.
All right.
Yeah.
Sorry, just one other question.
Yeah,
So,
sure.
So transpose convolution, I understand it's equivalent to probably say convolving with a stride of less than 1.
Yes,
correct?
That's correct. Yeah.
Okay, got it.
Yeah. So the flattened layer, it does not have any points, but this is going to get tested when you build your entire CNN model towards the end. Next up, we'll be looking at pooling. So there are two. So pooling actually does not have any weights. So it is just going to look at a window in your input, and it is going to do like some kind of a downsampling operation in this case. So that is done by using either of the techniques, which is max pooling or mean pooling. So in max pooling, you will look at the window, you will pick up the max value, and that's going to be plugged in the output map. So in case if you have one or more values that are max within a given window, then you will have to pick the value that comes first if you're using the row measure ordering, which means you traverse through the rows and then like through the columns. So yeah. For mean pooling, you will have to look at the window and take an average of all the elements. That's what it is. And you can see these sample outputs in order to check like how it works. For max pooling, make sure that in your forward pass, you would have to keep the maximum indices, which you would be utilizing in the backward pass in order to get back your DLDA. So in this case, say if the DLDZ is such kind of a matrix, and your max indices are these that you've obtained from your forward pass. So you can see that the index 2,0 actually has contributed 3 times to your output. So basically, when you go back, you're just going to sum up all of the contributions from the input. So make sure while you implement, you don't forget that plus equal to operation that the professor might have been mentioning in his lectures. So yeah, so this is all about mean pooling and max pooling. So even mean pooling backward. So all of the inputs are going to contribute equally. So when you go back, you have to again take the same thing into consideration. So all of the pseudocodes and the explanation that you need for these 2 layers are there in the lecture slides. So please carefully go through it. They make a lot of sense and it'll make your life easier while implementing these classes. So the last thing that we would be looking at is implementing like CNN as a simple scanning MLP and as a distributed scanning MLP. So both of these techniques have been clearly mentioned in the class. So you have been given something like this in your code, and you will have to figure out what these convolution layers are, what are going to be the in channels, out channels, the kernel size and the stride that you would have to give for these convolution layers. You also have the weights. These weights are going to be the MLP weights. So you will have to do some kind of a transformation of like some reshape or resizing of your weights so that you can use it along with the convolution layers. So this is the case for MLP. This is the case for CNN as a simple scanning MLP, wherein you will have to utilize your weights and just reshape them. In case of distributed scanning MLP, we know that it's a shared parameter network, and the distributed scanning MLP is going to have much lesser parameters than our regular MLP. So this structure is again going to be something similar. You will have to figure out what these convolution layers are, what are going to be its in channel, out channel, kernel size, and the stride. Now looking at the weights, these are the MLP weights, and we are now implementing a distributed scanning MLP. So the weights that you would want to use might be some smaller portion of the actual weight. So you might not require all the weights. So you need to figure that out depending on the inputs to the convolution, like whatever in channel or out channel or whatever kernel sizes. Depending on that, you will have to pick up those particular elements or slice your weights accordingly in order to use it with these convolution layers. So these two functions can get tricky sometimes. So I would recommend you to actually use the pen and paper and draw it properly and understand what could be the sizes that your convolution layers would take in. So the last point is building a CNN model. So all of the details of the CNN model are given here. You would not be implementing, not be using pooling layers in this particular model. It's just the convolution layers and the activation functions followed by the last linear layer. So this linear layer is something that you've implemented in your previous homework. So yeah, you would be using that. Also the activation functions. And you could use this CNN model for your homework too, part 2 also for training. So yeah, all the best with your homeworks. And if you have any questions for part 1, please go on. Or else we can move to bootcamp for part 2. Okay, great. I think David, you can start with the part 2.
All right.
Yeah.
Sorry, my PowerPoint is loading. All right, can everybody see my screen? Can anyone see my screen?
Yes.
Great, okay. I'll try to monitor the chat, but then probably, yeah, just put questions in the chat if you have questions. All right, so this is the homework 2 part 2 bootcamp, and let's go through some logistics first. So early submission for this homework is due tomorrow, 11:59 p.m. EST. Please make sure to do the early Kaggle submission for both the classification and the verification, as well as the Canvas multiple choice questions to avoid losing points for this. You'll need at least a 5.5% in classification and then a 0.75 AUC in verification to pass the cutoff, the very low cutoff. The on-time submission is a bit later. I believe it's March 17th. And then homework 2 part 2 is significantly harder than homework 1 part 2. Models will be harder to train. It will be harder to code the models. It'll be harder to train and then converge. So please start early. And for this homework, you're limited to 35. These slides are not online, but we'll post them right after the bootcamp, along with the code. So for this homework, you're limited to 35 million parameters. And exceeding this limit, I say will incur a penalty, but you're not allowed to exceed the limit. So it'll be a very harsh penalty. Models must be written yourself and trained from scratch. You're not allowed to use pre-trained weights, etc. And yeah, those are logistics. Are there any questions for logistics? And let me just double check the due date. Yeah, okay. Due date is correct. And yeah, let's get started.
I have one small question.
Okay.
Models need to be trained from scratch, but we can inspire ourselves on existing models like VGG or ResNet and stuff, right?
Of course. So what we mean by scratch is you're not allowed to pre-train your model on ImageNet and then load those weights and then fine-tune our data set. Because that would kind of defeat the purpose of like getting to know and how to train models from scratch.
All right. Okay. Thank you very much.
When will the cutoffs? The cutoffs will be released after the early deadline. So tomorrow or over the weekend. Can we use Model Zoo? But no, you have to code the models from scratch. So you have to code class whatever model nn.module and then write everything yourself. All right. We can use you can use weight initialization methods. All right. So this problem is divided into two parts. First is face classification, which is classification you're already used to from homework 1. So you're given an image, figure out what person it is. And I believe there are 7,000 identities, and you're just figuring out which person it is. For face verification, you'll be given 2 images, and you want to figure out whether they belong. Those are images of the same person or they're different people. The pipeline is going to kind of look like this. So face verification, you have an image. You're going to put it into a feature extraction model. This is otherwise known as the backbone, which generates a feature embedding, which is an n-dimensional vector. That goes into the classification linear layer, which generates the number of class probability logits, softmax, and then you get your probabilities over the different people in the data set. So this final one here will be length 7,000. And then the actual length of this embedding vector will depend on what model you're using or designed. Now, having trained this face classification model, you can use it for face verification. So notice that we just removed the linear layer here. Now we're given 2 images. Here, they're of different people. We get a feature embedding, so a feature vector for each. And then you compute cosine similarity, which returns a similarity score between -1 and 1. And as for what cosine similarity is, it's this formula. It's not a complicated formula. It's basically just the normalized dot product between these 2 feature vectors. So if these faces are very similar or they're of the same person, we would hope that the feature embeddings of these 2 images are similar, which would cause their dot product to be large and close to 1. If they're of 2 different images like we have here, we want their dot product to be negative, so very different. And we would have -1. So 1 indicates similarity, -1 indicates dissimilarity. Is there, yep, okay. Great. So the workflow that you're probably going to follow for this homework is first, train a strong classification model for the classification task. Then for the verification model or verification task, use the model trained on classification and then get rid of the final linear layer, or basically take the penultimate features as feature embeddings of each image. And I say get rid of the linear layer, but sometimes it's possible that the final n-class probability logits are also a sufficiently strong feature embedding. So you can try experimenting with both using this or this. Finally, if you find that your verification score is not good enough, you can additionally train the verification specific losses, such as arc phase, triplet loss, to improve performance. And we'll be releasing starter code for triplet loss as well to facilitate this. Are there any questions up to here? Because the rest of the slide kind of builds on this. Why don't we calculate similarity with the final output layer, softmax layer? Why? I guess you could. You could. I believe it's going to be worse, or at least similar performance. There's no real point to doing so, because
I think it is because it has to work for more than the 7,000 faces.
Right. So that's right and not right at the same time. So yes, Intuitively, it doesn't make sense because after the softmax, you'll have a probability distribution over the 7,000 classes, and you're working with images outside of the 7,000 classes. However, at the same time, that probability distribution itself contains some inherent information about the image. So you could say this new person kind of looks like 50% person A, 50% person B, etc. But you should use the features from before the softmax. Is it proper to set 0 for cosine similarity threshold? Okay, that's a good question. You should not threshold the similarity score at all. So you're gonna output -1 to 1. Just directly put that as your similarity score and submit it to Kaggle. And the verification AUC, you should look it up how the metric actually works. There's a lot of good articles. Takes into account the confidence of the similarity prediction as well. So you should not threshold. Can you briefly explain high level what these verification specific losses are? Okay. We also do have a recitation on this tomorrow. There's a lot of overlap material between the bootcamp and the recitation, so maybe they'll go into more detail on this. But basically, arcface is a supplement to the classification method. I wish I had a diagram for this, but classification, the standard cross entropy loss, if you think about like a 7,000, okay, I don't know how you would think about a 7,000 dimensional space, but basically you can think of a dimension with 7,000, a space with 7,000 dimensions, and then each model prediction is going to be somewhere on the 7,000 dimensional space. And then arcface kind of tries to push away different clusters on this hypersphere in 7,000 space. So the goal is to make the feature embeddings more discriminative. So the boundaries between different classes are more separate, and that improves the verification test. Triplet loss follows the same principle. So triplet loss, you have an image of class A, another image of class A, and then an image of class B. And the idea is to pull the features of the same class together and push the features from different classes apart. And then again, this enhances separability, linear separability between different feature embeddings, which is also beneficial for the verification task. For two completely opposite faces, would the match score be 0 or -1? So it's not obvious what completely opposite faces means, but the match score would be -1 because -1 indicates dissimilarity, 1 indicates similarity. If I need to proceed with the test procedure, shouldn't I set the threshold because there's no label? So if you were to actually use the verification model in like some downstream real world task where you're given two images and say, are these two images similar or not, or same or not same? Then you would need a threshold. However, for the evaluation metric evaluates at a bunch of different thresholds. So you need to actually give them the raw confidence values give the metric the raw confidence values to calculate the metric. And yeah, Rami has a good answer for this. All right, so let's get to the main point of the bootcamp, which is architectures. So at this point, I'm assuming basic familiarity with convolutions as taught in lecture. However, as individual convolutions can be assembled into a strong architecture in so many different methods. You have to consider the number of layers, the channel sizes in each layer, the strides, kernel size, etc. For this bootcamp, we'll cover 3 architectures: Mobilenet V2, which is a fast parameter efficient model. ResNet is the de facto go-to for CNNs. If you have a 2D problem, you just first start with the ResNet. However, it is larger than the Mobilenet variants. So that's why we're giving the code for Mobilenet. Convex is the state-of-the-art model. It was released like 2 months ago and it has good performance. And outside of these, you're entirely welcome to try other models. And then I have a list of different models you can try at the end of the slides. But these 3 architectures are the ones we've most verified that works well on this data set. So we are recommending them. All right. So these general architectures do have a formula. So architecture is the model architecture is divided into stages, which are then divided into blocks. Each stage consists of almost equivalent blocks, and each block consists of a few CNN layers, background layers, and relers. The key innovation or the differences between models rely in the differences between blocks. So there's a Mobilenet block, there's a ResNet block, and a ConvNext block. So to understand the paper and its architecture, we just need to understand its blocks. And all that changes for the same block in different stages is the base number of channels. And what that actually means is the general flow of a model goes stem, and then a bunch of stages, and then a final classification layer. And what these different components are is the stem is usually just initial processing on input. The input is an RGB image of 3 channels, and you generally want to embed that into higher space, like 64 channels, etc. And the stem also usually downsamples the input spatially by 4 times. And I know that students were confused about this in previous semesters. When we say downsample, we are referring to the spatial resolution. We do not say downsample when we decrease the number of channels. We just say decreasing or increasing the number of channels. So the stem usually downsamples the input by 4 times because at like a 4 pixel region, it's basically just like low level information that you can just squash. Some stages do downsample. We have n stages here. If a stage does downsample, generally the first convolution in the stage downsamples by 2 times, and the rest are just maintain the same spatial resolution. When you downsample by 2 times, you also increase the channel dimension by 2 times. If you've taken a look at the starter code, there is some intuition in the comments there, but basically you're losing information by downsampling 2 times. So let's take that information away from the spatial resolution and then put it in the channel dimension. So you're not really losing information anymore. So by virtue of this, later stages, later stages have smaller spatial resolution, but they have a higher number of channels. And intuitively, you can think of it like you're reducing the spatial resolution, but you're going up in the semantic level. So later stages capture higher level information like different objects and stuff, while the earlier stages just focus on edges, corners, etc. Right. So are there any questions up to here? Because we'll build on this intuition. Yeah, these slides will be released after the bootcamp. All right, there are questions, I'll proceed. The goal of Mobilenet, so we'll go through Mobilenet first. The goal of Mobilenet is to be parameter efficient. And there's a question. Will you be talking about the whole padding to maintain the spatial resolution in the handout? Okay, yeah. So I'm glad someone mentioned this. There was some confusion about this. I guess the comments were sufficiently clear. Basically, in the handout, it said, figure out the padding so that the spatial resolution does not change. What we meant by that is, assuming there is no stride, you can figure out the padding required to maintain the spatial resolution. So if I give you an image of resolution 10 by 10, after the convolution layer, the result should be 10 by 10 with no stride. And that requires a specific padding value dependent on the convolution kernel size. Now, given an image of spatial resolution 10, with stride 2, we would expect that the output is 5 by 5. And that requires the same padding value. And that's the padding value that we want you to figure out. And the padding value should be like single digit numbers. We've had some students put in padding values of like 100 something to maintain the spatial resolution. That's not right. All right, great. Okay, Mobilenet. Okay, what does with no stride mean? So with no stride means stride of 1. So you're not downsampling at all. I did not catch what stem is. So stem are just a couple linear layers before we get into the bulk of the model, the different stages. It's like usually 2 or 3 linear layers with some Batcherman ReLUs between. And it's basically just a small group that projects from 3 channels to 64 channels or whatever number of channels. And then it also downsamples the spatial resolution by 4 times. If your filter had size 200, 100 could be right. I'm not sure what you mean by that, Kellen. If you could explain. Could you explain why the input usually 4 times downsamples? Yes. And that's because if you look at a 4 by 4 pixel of a standard real world image, it's usually, there's not much meaningful semantic information there. It's usually very low level details, like maybe you see an edge, some color information, a corner, or not even a corner at this point, So downsampling by 4 times early on reduces the computation cost of the model. And it also, that's basically it. And there's not much information that can be gained by pouring more computational costs into these low-level pixel information. All right, I do want to move on because we do have a lot of slides. Are the TAs still here? Okay. If the TAs that are here could monitor the chat and just like type responses, that'd be great. Okay. So Mobilenet, okay. I did ask for clarification, so I'll take one more question. You mentioned that by some students padded by 100. Wouldn't the correct amount of padding to maintain the output size of convolution using a kernel size of 201? Yes, that's correct. That intuition is correct, but the kernel sizes that we're working with is like 3 or 7, so it doesn't make sense to pad by 100. Great. Mobilenet. They make the model parameter efficient by making extensive use of depthwise convolution and pointwise convolutions. As for what these are, we did cover depthwise convolutions in the lecture, I believe today or the day before, but we'll do a review of that. So this is what a normal convolution looks like. So the 3 dimensions here are, this is height, this is width, and this is the channel count. And a normal convolution, to get a single value here, basically applies this kernel on this entire region and gets a single value. And you should be very familiar with this at this point. And then if you consider multiple channels, the same process is repeated with a lot of different kernels to get the various output channels. And this is another diagram. Depthwise convolutions, and in shorthand for depthwise separable convolutions. And it's called that because if you consider the various channels as depth, you perform convolutions on them independently. And what that actually means is you have a convolution kernel with channel size 1. So it's just operating on a single channel at a time. And to get the output for this output channel, so looking at the orange channel here, to get that output value, you only look at the first channel of the input. And yeah, that's it. To get the red one, you look at the second channel here. And to get the yellow one, you look at the third channel here. And when I say look at is, I mean, you apply a convolution over just that single channel single channel feature map. So it'd be of shape H by W by 1. And since you have an input channel of 1, you also have a kernel channel 1. And this can be considered spatial mixing because you're basically just operating over the spatial resolutions without mixing different features or different channels. So again, the takeaway here is the convolutions are performed independently for each channel and they're performed over different spatial locations. And try to illuminate that, looking at this diagram. So this is basically the same diagram, slightly colored differently. And then if we look at our actual video of this, so yeah, if you remember in normal convolutions, you squashed or operated over all the channels at once, but for depthwise convolutions, you operate on each channel independently. And that's the key point. Are there any questions on depth convolutions? This is a bit of a different intuition from regular convolutions, so I want to get this clear because it's very important for the later models. What's the advantage? We'll cover the advantages. Hold tight for a second on that. Yeah, okay. That's a spoiler, but it's less computation, and that's the advantage. Any questions on how it actually works? The output will be the same for both, though, right? Yes. Yes. So for depthwise convolution, the input number of channels is the same as the output number of channels. Could you go over it again? Okay. I'll go over it briefly. So basically, you have an input feature map of size H by W by C. Here, C is just 3. Your output feature map is also H by W by C. And there's a 1-to-1 correspondence between the input channels and the output channels. To get the output channel number 1, you only work on input channel number 1. To get output channel number 2, you only work on input channel number 2, and so on. And by work on, we mean applying a convolution of shape 5 by 5 by 1. So 1 indicates that you're just convolving with one feature dimension. Does that make sense? Okay, great. Yeah, this is a very key point. So, and it's getting more and more use over the past couple of years. So it's very important to understand this. All right, pointwise convolutions. So depthwise convolution and pointwise convolutions can be considered two extremes. Pointwise convolutions are called pointwise because each pixel is now considered independently. So previously, remember that depthwise convolutions considered each channel independently. Now we're considering each pixel independently. So the convolutional kernel looks like this. And then you basically mix all the channels for that single pixel and get a single pixel output here. And then this is visualizing just a single output channel. Of course, you can do this for a lot of output channels. So you have a bunch of these different convolution kernels and you have this result. So to summarize, what we covered is a normal convolution mixes information. And I keep saying mixes, but it's basically the region that a convolution is applied over. A normal convolution mixes information from both different channels and different spatial locations. A depthwise convolution only mixes information over spatial locations. Different channels just do not interact. A pointwise convolution only mixes information over different channels. Different spatial locations do not interact. So you can see that depthwise convolutions and pointwise convolutions are opposites. And the intuition here is that a normal convolution, which mixes over two things, can be divided into depthwise and point convolutions. So instead of mixing different channels and different spatial locations in just one step, let's first mix spatial locations and then mix channel locations. And when you put those together, it's basically the same thing as mixing both channels and different spatial locations at once. However, the advantage is that each of these operations are cheaper and they have fewer parameters. And that's the intuition that Mobilenet built on. Are there any questions for this? On slide 20, how is the output not just one channel? This is just for visualization. In reality, you have a bunch of these different kernels. The output channel is 256, so you have 256 of these kernels that are outputting a single channel at a time. So yeah, it's a bit off visualization-wise, but yeah. All right, Mobilenet. Again, to understand our architecture, we just mostly need to understand its blocks. And this is the block of Mobilenet. It consists of 3 steps: feature mixing, spatial mixing, and bottlenecking channels. So we'll go through these one by one. So the feature mixing basically is a pointwise convolution that increases the channel dimension by some expansion ratio. And we call this feature mixing again because pointwise convolutions don't consider different spatial locations. They only look at the different channels in that pixel and then mix the features. And then increases this channel dimension by an expansion ratio. So if the input number of channels is 64, maybe this gets increased to 256. And you can see that the channel dimension here gets a lot thicker after you apply the pointwise convolution. And as for why you might do this, some relationships that are not very clear in low dimensional space become very clear in high dimensional space. And that's why you're increasing the number of dimensions or channels. After this is spatial mixing, a depthwise convolution that communicates information over different spatial locations. So now we have a lot of channels, but these different channels don't interact with each other. For each channel independently, you do a 3 by 3 convolution to get the output for that corresponding channel here. And that's basically it. We've covered depthwise convolution, so we're just applying that concept here. And this is called spatial mixing because, again, the different channels do not interact, the different spatial locations do. Finally, we want to reduce the number of channels, and we do that with another pointwise convolution that does the opposite of the expansion. So we now have a channel dimension of 256. Let's reduce that to 64 to make the computation more manageable. And you will notice that this 3x3 depthwise convolution, and intuitively you can think of like a 3x3 convolution being a lot more expensive than a 1x1 convolution. So we do the 3x3 convolution here, and we do it per channel, and that's why Mobilenet is more efficient. It doesn't use a normal convolution over all channels. It does it independently for each channel. So since 3x3s are expensive, it's cutting down on the computational cost of this section. Now we covered Mobilenet, which is basically feature mixing, spatial mixing, and bottlenecking channels. And we'll briefly go through the code for this, which the actual code won't be released, but the comments will. And the hope is that you'll implement the specifics of these 3 different parts by yourself by looking at the bootcamp. All right, hopefully you guys can see my code now. Great. So this is a single block in Mobilenet, and I have a lot of comments. I'm not going to go through them in the interest of time, but I recommend that you go through these and read them because they have a lot of intuition that will help you on developing later architectures as well. So this block takes in input number of channels, the output number of channels, the stride, and the expansion ratio. And the expansion ratio, again, is the expansion of after the first feature mixing pointwise convolution. I'll answer that question in a second. So the first feature mixing convolution is very simple. So you take the number, the hidden dimension is the input number of channels by the expansion ratio. So this would be like 64, maybe this is like 384 or something. Feature mixing is just a single convolution that takes in the input number of channels and increases it to the hidden number of channels. And you will notice that the kernel size is 1 because it's a pointwise convolution. The stride is 1 because we don't want to downsample here. And the padding is 0. And then we have the batch term and reload. Now spatial mixing here is the hidden number of hidden channels, which is very large, going through hidden channels here. And the kernel size is 3 because we're mixing spatially, so 3x3 convolutions. Padding is 1. The stride, if we were to downsample, so remember that we said that some blocks do downsample, and that downsampling operations happens at the 3x3 spatial mixing in Mobilenet. Groups is how PyTorch implements stepwise convolution. And the number of groups is the number of channels here, because basically we're applying, we're working over different channels on its own independently. So, and groups basically indicates, groups equals hidden dimension indicates that each channel we're working on its own. So you can read the documentation for that. You can vary the number of groups, but that's something you can explore. So spatial mixing was a 3x3 depthwise convolution. Bottlenecking channels, we take the hidden number of channels and decrease it to the out number of channels. And note that we have a separate variable name for in channels and out channels, but for Mobilenet, generally the number of input channels and output channels are the same. And again, this is a pointwise convolution with kernel size 1 and stride 1, and then we have the batch term layer after it. And as for the forward pass, we have feature mixing, spatial mixing, bottleneck channels. And we got a question asking, why is it called bottlenecking channels? And the intuition is, so we were working on the very high dimensional space. However, we want to take that high dimensional space and condense it. So you can kind of think of it like taking a very sparse dimensional space and distilling it into a more condensed, rich feature dimension. And you can force the model to make do that distillation by reducing the number of channels. And that's why it's bottlenecking it. Will this or the notebook have been shared? So this file has not been shared. It will be shared after the bootcamp. You'll basically get this exact file without these code. You'll get the comments, and the hope is that you'll read through these comments, watch through the bootcamp, and then fill out these sections. And as for the forward paths, we have feature mixing, spatial mixing, bottlenecking channels, and then we have a identity connection. So we add the input with the output. So that was a single block. And as for the Mobilenet itself, it's basically these different blocks put together. This is a stem that we talked about. It basically is just a couple convolutional layers that projects the 3 input channels to 16. This is just a formula for the various stages. So each of these rows represents a stage. Whoops. And in each stage, we specify some information controlling what that stage is going to look like. So each stage is going to have an expansion ratio of 6, a number of input channels of the number of blocks in each stage, which is 2, 3, 4, 3, etc., and the stride of the first block. So wherever the stride of the first block is 2, you can see that we're downsampling. And when it's 1, we're not downsampling. And notice that the number of channels increase at the later you get into stage. And the hope is that later stages capture higher level semantic information, which requires more feature channels. And then this is just a loop generating the various blocks. I recommend you go through this and understand it. And then some final feature mixing. And then this is the final classification layer. So adaptive average pool over the spatial dimensions, and then projecting the final channel number of channels to the number of classes we have. And in our use case, the number of classes is 7,000. These are the initialization parameters for Mobilenet. I just basically used what the paper suggested. These don't necessarily work for every model, but usually the model is generally robust to whatever initialization you use. And the flow of the model is to go through the stem, the various layers with the stages, the final block, which is just it's just a simple convolution, and then the classification layer. All right, this code or this file will be released, and you should fill it out and just run Mobilenet on the code. And since we gave you the starter code, it's just a plug and play, and it should be fairly straightforward to incorporate this into the notebook. All right, are there any questions up to here? We'll cover the other 2 architectures here. All right, looks like there are no questions. We'll go on to ResNet. Again, remember that to understand the paper, we really need to understand its blocks. ResNet proposes 2 blocks, basic block and bottleneck block. The key point in ResNet is actually the residual connection, hence the res. Actually, however, ResNet is older than Mobilenet v2, so Mobilenet v2 already inherited a lot of the intuitions from ResNet. But the reason we still have a distinction between Mobilenet and ResNet is that they have their own advantages. Mobilenet is very fast, and you can just use it for quick training. And ResNet operates on larger number of parameters. So Mobilenet is like maybe like, I want to say 7 million parameters, or 10 million parameters, and ResNet scales up to 10 million, 35 million, 100 million, etc. And this is the very basic building block of residual network. So the ResNet consists of 2 different blocks, basic block and the bottleneck block. And we'll cover basic block first. And compared to what we just went over at Mobilenet, since ResNet is an older paper, it's much simpler. So you have your input feature of 64 channel dimensions, and you basically just have 2 3x3 convolution layers. These are just regular convolution layers followed by batch term below each. And then there's a skip connection adding the input and the output. So you have 2 pathways here. One goes through these 2 layers, and another is just the identity connection here. And the reason you have this addition here is basically ResNet introduces this residual connection to help with learning, and then reduce gradient vanishing or gradient explosion. And the intuition is that if you have a bunch of layers just stacked, the gradient needs to propagate through every single layer here. And each layer adjusts the gradients a bit, but then it can end up reducing the gradients so few to like 1e -10 or something. So the very input layer basically is not getting any learning signals at all. What this residual connection does is it basically gives a highway for the gradients to very quickly backpropagate. So this gradient propagation might be like a factor of 0.1 on the magnitude, but this is just an identity connection, it's just 1 times. So this facilitates learning as well. Question, is this like bagging? Let's see, is this like, not exactly. And the intuition that you should take away from this is that you're taking the input features and just changing it by a little bit every time. So you have the input feature here, and you're like, hey, let's take this input feature and just learn a residual. Let's just learn a couple of different things we changed the input and add it. So maybe the input feature is like 1.0, and then the residual connection is 0.2, and the final output is 1.2. So this is just a bit of extra modifications that you do into the input to get it to where you want. And that's the intuition you should carry over from this. The bottleneck block is basically the same thing, with the inside being a bit more complicated. 256 channel input goes through a pointwise convolution, now reducing channels to 64. A 3x3 regular convolution maintains channels at 64. Then a pointwise convolution expands channels back to 256, and then you have the residual connection. And now that we're familiar with Mobilenet, this should seem kind of familiar and also not that complicated. And yeah, because Mobilenet came after ResNet. As for the overall architecture flow, recall that we have this kind of standard formula for different CNN architectures. So up to here will be considered the stem. This will be stage 1, stage 2, stage 3, stage 4, and then you have the classification layer here. And some people find having like a visualization of the model helpful, and this is a visualization for the paper itself. So this would be the stem, stage 1, stage 2, stage 3, stage 4, and then the classification. And again, for a lot of these, I strongly recommend taking the time to go through and read the paper. ResNet is a very good paper, especially if you're new to deep learning. Mobilenet is a bit more involved, but there's a lot of good intuitions in there. And ConvNext, which we'll cover later, is fairly easy to get through. So are there any questions on ResNet? What is the advantage of the pooling layer at the very first ResNet model? So what is the advantage of the pooling layer? The purpose of the pooling layer is just to reduce the spatial resolution. And because the reason we even reduce spatial resolution is twofold. First, to decrease computational costs, and second, to increase the receptive field. The latter is already explained in the STAR notebook. So to cover the former, if you have a feature map with a spatial dimension of 100, or spatial resolution of 100 by 100, and a channel dimension of 32, and compare that with 50 by 50 with 32, you can intuitively see that doing convolutions on this will have 4 times the computational cost as this, right? And that's why we have a stride 2 layer early on to quickly reduce the number of spatial resolutions from 100 to 50. And the reason we can do this is our assumption is that early on, when you're working with like just a few pixels, the early downsampling early on doesn't lose a lot of information, because if you look at each, if I gave you just a single pixel, there's basically very little information. If I gave you a 2 by 2 grid of pixels, just 4 pixels, if I gave you 4 pixels, you would also similarly not be able to get a lot of information out of it. So what the intuition is that we can just collapse these 2 by 2 pixels into just 1 by 1 pixels early on without losing a lot of information. And what we gain from that is a lot of computational cost savings. I did ramble a bit there, but did that make sense? Or did you have any other further questions on that? Okay, great. Now, ResNet at this point, I believe it's a 2015 paper. Mobilenet is a 2017 paper. And then from then to now, there has been a lot of improvements in architecture. And ConvNext represents the state-of-the-art performance in image classification right now. And I believe this was released a couple months ago, so it's very, very new. However, the interesting thing is ConvNext intuitions are very similar to that of Mobilenet, and we'll see this in a couple of different slides. And remember that to understand a paper, we just really need to understand its blocks. And unlike ResNet, there's just a single block type for ConvNext, so it's very easy to implement. And you should read the paper for details on stages, channel sizes, etc. And we recommend the ConvNext convex t referring to tiny size for our homework, which is under the 35 million parameter limit. And yeah, so basically how we want you to go about doing this homework is we basically give you the ResNet code. We basically give you the Mobilenet code. And what that code contains is it's a framework to have some kind of block and then repeat that block over different stages according to the parameters you set. And then what you're going to be doing when you implement ResNet is you're going to be changing that block and then putting that changed block into the same framework as Mobilenet, but you'll change the parameters. For convex, you'll again implement a different block and then feed that into the different stages, etc. So what you're really going to be coding are the different blocks, and the general plugging that into different stages will be similar. A bit different because the number of channel sizes and the number of stages are different, but the core innovation in each method are the blocks. And that's why I keep reiterating this. All right, this is a complex block with the ResNet block on the side for comparison. And the complex block consists of 3 parts or 4 parts. First is a 7x7 depth-wise convolution. Next is a point-wise convolution, increasing the number of channels. And then a point-wise convolution, decreasing the number of channels, and then a residual connection. And then you notice that we have some normalization here and the activation here. And that's basically it. And you'll notice that this is very simple. You can definitely just go off and implement this quickly. And we recommend you do so because convex is very well in our data set. But you might also notice that a lot of these components are very familiar. And that's because convex and Mobilenet are very similar in the general intuitions they encompass. So I have them side by side. I'm not going to go through this again, but these are different components. So we have the spatial mixing still. So in Mobilenet, if you remember, the spatial mixing was a 3x3 depth-wise convolution. Now in convex, it's a 7x7 depth-wise convolution. And the intuition is spatial mixing, you just want to mix features or mix different spatial locations together. And why do that with the 3x3? Let's just increase it to a 7x7. So you can just look at a lot more locations at once. Next is feature mixing. We have a point-wise convolution that increases the number of channels, exactly the same. Next is, whoops, I accidentally deleted a slide here, but the one thing I wanted to show was this is bottleneck. This is the bottlenecking channels, which is a point-wise convolution decreasing the number of channels. You can see that it's exactly the same for Mobilenet and convex. All that's different are the ordering. So you have the same 3 components, just ordered in different ways for convex, and they're extremely similar. Of course, since convex is light years ahead of Mobilenet in performance, there are some differences. So what changed? The depth-wise convolution is a larger kernel size, 7x7 as opposed to 3x3. However, increasing the kernel size from 3x3 to 7x7 isn't free, which leads us to the next point. The order of spatial mixing and feature mixing are flipped. So you see this cross here. So these 2 are flipped. And the reason you do that is because 7x7 is a lot more expensive than 3x3. So Mobilenet increases channels before applying the 3x3. So the 3x3 convolution here is working on a very high channel size of like 384 if the base was 64. Convex instead has the 7x7 first. So it's working on a smaller channel dimension of 64. And after doing the spatial mixing, it increased the channel dimension to 384. And that's the push and pull here. We offload computation away from the number of channels into the spatial resolution of the kernel size in the spatial mixing. Does that make sense? Are there any questions on that? Because that intuition is very key on what's different between these 2 models. Great. So that's the key. Why is 7x7 more expensive? So if we kind of think about, so what a convolution is it's basically you have a kernel and you're just, if this is a feature map, you're just scanning it across the H and W. at every location, you do a element-wise multiplication between the kernel and then the same resolution on that feature map. So to phrase that a little better, if you have a 3x3 convolution, at the first spatial location, you're doing element-wise dot product between the 3x3 of the kernel and the 3x3 of the feature map. And if you understand that, you can kind of see why increasing the kernel size to 7x7 would dramatically increase the computational cost as well. Because now you're doing a dot product between basically a vector of length 9, 3 times 3 is 9, to 49 here. So basically what you've done is you've increased the computational cost just from this by 5 times. Does that make sense? Great. Clear. Yeah, so that's the difference there. The other difference is Convex uses layer norm. Mobilenet V2 uses batch norm. Convex using layer norm, if it's a bit weird, we strongly recommend you use batch norm for this homework regardless. Layer norm, if you look at the paper, isn't the key factor in improving their performance. And we find that it's very hard to converge on our data set. Convex also recommends training via Atom W. Mobilenet V2 recommends SGD. Again, this being an introductory course in deep learning, we strongly recommend using SGD for this homework because it's easier to optimize for image models. So you the same training parameters for Mobilenet and ResNet, we could just directly put that onto Convex. And this applies to weight decay as well. So learning rate, weight decay, momentum, whatever, we recommend using the same ones you use for Mobilenet for Convex. Isn't SGD harder to turn in terms of learning rate? No. Or yes, but also no. No, because for 2D image classification models, this is extremely, extremely well explored. So there's a very good formula for what learning rate you want to use for what batch size. And that's the formula we provide in the STAR notebook. For an arbitrary problem with an arbitrary model that might be hard to learn, Atom generally performs better because Atom has the adaptive thing that gives the different learning rate for each parameter, etc. But for 2D image models, SGD is just simpler with fewer bells and whistles. Great. Again, one last difference is Convex has fewer batch norm and ReLU layers. So in a ResNet, you would have a batch norm and ReLU layer after every single convolution here, and a batch norm and a ReLU. What the guys at Convex found was that it's actually better to reduce the number of such batch norm and ReLU layers. And so they just have a single batch norm, not even a ReLU here, and they have a GLU, which is basically a more advanced ReLU. And we recommend you strictly follow this formula. Or actually, you can try modifying it and then exploring with different ones. Convex being a very, very state-of-the-art paper, I think it'll be difficult to make any substantial improvements on it, but it is fun to explore, and that small improvements still can improve performance. What is layer norm? Why aren't we using it? Please remind me. Let me cover that at the end because we do have a couple other important things I want to get through first. Others. So, okay. Are there any other questions on the core architecture for Convex? Great. Now others. And unfortunately, the state of image classification is so that the others are very important. So the first part of others is data augmentation. Data augmentation is extremely, extremely important. You will find that you have the Mobilenet code, and then you ran the Mobilenet model and you have a performance. And then you move on to ResNet or Convex, and then you run the code and you find out, hey, the performance is the same or even worse. And that's because the larger model or the more advanced model is severely overfitting on the data set. And you should definitely look into the torch vision transforms library here. And some of the things we recommend are color jitter, flipping horizontal left, right, resized crops, affine transforms, this thing called rand augment, which is generally a good plug and play augmentation cocktail. And we recommend you try different things out. And you'll find that the models are very, very sensitive to different data augmentation strategies, which is a bit unfortunate, but it's just the state of how things are. Data augmentation is on the train set, not the validation tests are correct. So we should see much lower accuracy on train than validation. Yes. So after you apply data augmentation, what you'll notice is that training accuracy will go down. Hopefully, validation accuracy goes up. So it's closing the gap between training accuracy and validation accuracy. However, just because the training accuracy went down doesn't mean that the validation accuracy will go up. You'll find that with some augmentation, both training accuracy and validation will go down, which is not something you want. And with stronger augmentation, you generally do have to train for longer, but some augmentations do allow for better validation performance in the same number of epochs. Why does training accuracy go down? It's because a very high training accuracy of like 99% means the model is overfitting, and the data augmentation reduces overfitting by kind of artificially increasing the number of images you see. So you have your image and you have a left-right flip version of it. So effectively you've doubled the size of your training set. And with more training set, it's harder for the model to memorize everything, which is why the training accuracy goes down. And when I say goes down, I don't mean goes down through training epochs. I mean, compared to without data augmentation, the training accuracy will be worse, but hopefully the validation accuracy is better. Did I answer your questions there? Okay. Great. Next, others. Monitoring training and validation accuracy. So again, this is a bit of intuition that's different from classical models. So the standard intuition of overfitting is that if the training accuracy and training and validation, if the training and validation gap is too large, you should stop training as it's overfitting. However, modern deep learning, this is not as relevant. And we find that a model can keep improving in terms of validation accuracy long after the training accuracy hits 100%. And there's recent research papers that finds that on some problems, we have training accuracy hits 100% at epoch 10, and the validation accuracy is terrible at 50%. And they train for 1,000 epochs, and the training accuracy is still 100, but now the validation is 100% as well. And of course, we can't train for 1,000 epochs, or we can't train for 10,000 epochs. But the intuition to take away from this is you should keep training until the validation accuracy stops improving. Just because the training accuracy hits 99% doesn't mean the validation accuracy will stop improving. Or instead of micromanaging your model, what I like to do, if I have some time, is just have a baseline setup. Like I'm just going to train all models for 50 epochs, just a standard cosine annealing LR scheduler, which basically looks like this. I'm not going to touch it until it reaches 50 epochs. And I do prefer this because it allows for more fair comparison over different settings, as opposed to you're like micromanaging your model. Okay, I'm going to stop training here. I'm going to decrease learning rate here. And then it's, I think, a better use of your time. Extras. And again, there are a lot of different tricks to improving your convolutional neural network. From the recent ComNext paper, this is a whole different list of things that they did. And I guess of relevance are these. What we do recommend trying first is, in addition to data augmentation, we do recommend label smoothing, which gives a huge boost. You can find details on what that actually means in this paper. Stochastic depth, it's a bit harder to implement, but basically the intuition is that you have like 50 of these stacked, right? And maybe you want each of these to do some work. So maybe this one's not doing a lot of work because you can just rely on these two to do a lot of work. So stochastic depth basically says sometimes let's get rid of some of these. So in the forward pass, usually you do every single one, but now you just have the residual connection here. And now this feature needs to do work because it can't just depend on the work done by the earlier convolution layers. Empirically, this adds a little bit of performance improvement. So it's something that you can try at the very end when you're like, I'm out of ideas. What's like a something I could just improve. You do to improve the accuracy by a little bit. So none of these state-of-the-art CNNs implement dropout layers. That's a very interesting discussion to have in and of itself. Yes and no. As with a lot of things, yes and no. So let me cover that and after I cover EMA. EMA you can look up. I don't want to get into it here because it's just an implementation trick. Dropout before the final classification layer. So you have the final feature vector from your backbone stages. You reduce the spatial dimensions, so you just have a feature vector, and you can have dropout there before you put it into your classification layer. And as for mentioning, yes, EMA is exponential, or not expected, it's exponential moving average. So do none of these models use dropout layers? A lot of them do use dropout layers here. However, using dropout layers between CNN layers is less theoretically supported, or it's likely to have less impact. Because if you think of it like this, if you have a feature map like this, and you just drop out a few pixel locations like here and here, because this feature map was generated by applying a lot of 3x3 convolutions, what ends up happening is the features at this location are very similar to features here. So the neighbor features are quite similar. So if you just drop out one here, the model can just look at the neighboring feature here and say, oh, I don't get any information here because it's dropped out. I can just cheat by looking at my neighbor. So dropout in this form is not very effective for convolutional networks. If you want to explore dropout for convolution neural networks, we recommend, I guess I'll put this here, drop block. This is the paper in and of itself. And the intuition is basically, instead of dropping on individual pixel locations, let's drop out patches like this. So it's harder for the model to cheat. Oh, I cleared that too early, but did that make sense? Yes, dropout after the final pooling layer. But if you want to put dropout between convolution layers, I recommend drop block instead of dropout. Yeah, I think that's good. Okay. All right, we're almost done. Then you can try the others, other stuff like mix up, cut mix, layer scale. Okay, don't try layer scale. It doesn't work if you have SGD. And then check out this bag of tricks for image classification. This is just a paper. It's just a technical report with a bunch of different tricks that you can use to improve your classification model. And of course, there are a lot of other papers besides these. You can just reference these. I want to say ResNext. ResNext is a strict improvement to ResNet, but it's slower. It's like 3 lines of code that you change. SENet, you can read the paper. It uses a tension mechanism. It's very interesting. It's like 20 lines of code. This is optimized model scaling. These two rather. This one likely requires a bit more effort. RegNet is a bit easier to implement, maybe like 10 lines of code change. This is very hard to implement. It's good performance, but it's very hard to implement. But you can treat it as a fun exercise, and this is doable. All right. Could you please explain the cosine annealing part again? Yes. So the cosine annealing learning rate, it's just a learning rate scheduler. So I think a lot of people have been using reduced LR on plateau, but that also has some parameters you have to tune, like patience, gamma. I think there's one more, but I forget. So cosine annealing LR just does away with all of that, and basically this. So this is your high learning rate, and this is like 0. And this is epochs. And recent research shows that cosine annealing LR can perform better than reducing LR at certain plateaus. Like in VGG, if you have multiple linear layers before classification, do we add dropout just before the classification layer? It's been a while since I've looked at the exact architecture of VGG. Generally, I think that's a relic of the past, perhaps. Basically, all models just have a single linear layer after the convolution layers, or single or maybe 2. You can put dropout between them as you want. Do fully connected layers after CNN cause us to lose shift invariance? No. And that's because of the average global pooling. Because shift invariance is basically the intuition of treating each spatial location the same. And the convolution embodies that concept by applying the same convolution to different spatial locations. The average global pooling collapses the spatial dimension entirely just by doing average pooling over all spatial locations. So you can see that that's not preferring or like doing something special for different spatial locations. So that preserves shift invariance. Cosine annealing works on batches if I'm not wrong. Batches if not. I'm not sure what you mean, or I'm not sure what the connection between batches and cosine annealing is, but it works over different training iterations, and each training iterations you process a batch, if that's what you mean. So it's just a learning rate scheduler. It's nothing special. It's even simpler than reason learning rate on Plateau. From what I read, the learning rate decays after each batch. Yes. Yes, it decays. So it decays like this, but the amount it decays by is very, very small, and then it suddenly decays here and then tapers off here. Yeah. So as for, yeah, I mean, that's it. You shouldn't overthink it. It's just another learning rate scheduler. You decay after each batch or each epoch. If you look at the code in the starter notebook, there is basically a parameter that cosine annealing LR takes in. It's like T max. And this parameter is basically asking you, how many times are you going to call scheduler.step for me to get the learning rate from high to 0? If you call scheduler.step after every batch, T max should be the total number of batches that you're going to be training from, 4, which is number of epochs times the number of training batches. If you're calling it after every epoch, then T max should be the number of epochs. So you can just control this as you want. I think standard practice is just decay it every batch. Can you briefly? Oh, of course. Yeah. Let's see. What's the best way to explain layer norm? All right. Part of my terrible drawing, but layer. If you remember batch norm, or maybe I won't draw anything, but let me explain it verbally and then see if you have any further questions. So the intuition of batch norm is to normalize features, each individual feature separately over all batches and spatial locations. Actually, there's a very good diagram. I could just copy and paste. All right, so let's look at this. So this is like a cube, not a cube. It's like a tensor with 3 dimensions represented, number of batches, number of channels, and H and W. And it might be a bit confusing to collapse H and W into just a single dimension, but batch norm and layer norm don't work differently over height and width. So you can just, that's why it's collapsed here. So batch norm computes the norm over each channel separately, normalizing over the various batches as well as the height and width dimensions. Layer norm is different. Layer norm instead normalizes over the channel dimension. And this diagram is a bit unfortunate because this, I believe, comes from a language paper, or no, it doesn't come from a language paper, but the way layer norm is used in CNNs is it doesn't normalize over the H and W. So actually it just normalizes over each channel dimension like this. So what you can kind of think of is you're basically making the channel dimension, each channel dimension vector into a unit vector because you're normalizing over it. Or no, that's okay. Scratch what I just said. That's completely incorrect. You're normalizing the features over each channel, over the channels into a normal distribution because you're subtracting the mean and dividing by the variance. And you do that over the channel dimension for layer norm, and you do that for each channel dimension in batch norm. Did that clarify your question? Okay. And as for why layer norm doesn't work on our data set, I really don't know. I think layer norm, I could not figure out why layer norm doesn't work on our data set. If you can get it working, please let us know because it'll be something interesting. But batch norm is proven to work very well on CNN, so we just recommend you use it for our data set. I think there was another question. Can you explain the important factors to consider to avoid overfitting? I think the learning rate seems to be the most important factor in preventing overfitting. Is there an appropriate way to select the learning rate or schedule the method? Okay. Preventing overfitting. Okay. I think this is somewhat of a personal opinion, but I think the phrase preventing overfitting is a bit of a relic from classical machine learning, and then it's a bit of an older concept. You should identify overfitting when it happens, and then work to increase the diversity of your data set through data augmentation. But preventing overfitting for the sole purpose of reducing your model's performance on the training data set doesn't make sense. That said, overfitting happens. And we went through a couple different strategies to increase the data diversity to try to improve the validation performance. And it's these methods. Or what exactly was the question? I think learning rate seems to be the most important factor in preventing overfitting. No, data augment, yes and no. Data augmentation is probably one of the most important factors in preventing overfitting or reducing overfitting. Learning rate is also an important factor. There is research that suggests that starting with a very high learning rate and then reducing it over time improves generalization when compared to starting with the lower learning rate. Is there an appropriate way to select the learning rate? If you're working on a new problem, you have to search it yourself. If you're working on a proven problem like image classification, you can build off of other works. Or scheduler method, most works just use cosine annealing because they don't want to tune. Can you briefly go over the starter notebook for us? It will help us with the early submission. Okay, I don't want to say no, but if you have questions on the starter notebook, it'll be better if you post on Piazza, because I think this bootcamp has gone long enough. And then a lot of the feedback we received for the bootcamp and homework 1 was that it was just merely going over the starter notebook. So I tried to include a lot of intuitions that will be helpful for understanding models and such. But yeah, just post on Piazza if you have any questions. And yeah, oh, I almost forgot, just a little thing because someone specifically requested it. Someone had asked what the difference between cosine similarity and Euclidean distances. Intuitively, cosine similarity cosine similarity is more related to dot product, and Euclidean distance is L2 distance. So if you think about a dot product between two vectors, it's A, B, cosine theta. So it's measuring kind of like this, how it's basically measuring similarity in terms of this angle. If they're similar, this angle is going to be small. If they're dissimilar, this angle is going to be very large. So that's cosine similarity. Euclidean distance instead considers just L2 distance between these 2 points. So the difference here. So cosine similarity is used because it's normalized between a certain range. Euclidean distance is something separate. And I don't want to get into the details, but there's a lot of there's a couple of articles explaining why you would prefer one or the other. Great. Yeah, I planned this for 30 minutes. I'm not sure how it ended up being this long, but if you have any other questions, come to my office hours or post on Piazza, etc. The starter for the first conversation with kernel 7 stride 4, there's not a whole number value of padding for which the spatial resolution remains the same. there is, I don't want to keep everyone here just to answer the question. Please post on Piazza. Another option is to try different padding values and see what happens to the spatial resolution, and you'll definitely find one for which there is no spatial resolution difference. And then from that, you can work backwards and say, why did this work? And you'll get some intuition for it. It's also covered in the lecture slides, but all right. Hopefully I didn't ramble for too long. If you have questions, post on Piazza, and thanks for coming to the bootcamp.